Hey everyone, welcome to another class in this AI journey. In today's class, we're going to talk about the thought process that's required to choose the best algorithm for machine learning or deep learning, right? Because this can be a problem of plenty. And many of you have requested me to make a video on this topic where you're confused about, how to go about this challenge of, choosing the best algorithm because you have too many options. Like you have linear regression, logistic regression, k-nearest neighbors, you have clustering algorithms, you have neural networks. So how do you go about this? So that's what we'll be able to discuss in this video today. So let's take the whiteboard and start the discussion. So here's the thing. There are many parameters that you have to take into account when taking this decision. So like a few things, basically, which you have to think about. They are interpretability, then performance and resource constraints, right? So the first question you have to ask yourself is that whether it's classification or a regression problem, right? So if it's a regression problem, you have like say your linear regression. You can also use your decision trees or random forest for this. And you can also use your neural networks for this. But then it's classification, you have say your logistic regression, you have again your support vector machines, you have your random forests, decision trees, and then you can also have again neural networks for this, right? And you can also have a k-nearest neighbors. So when do you use these algorithms? That's the main question, right? So the first thing is you have to start to think about the data. If your data is less, if your data is more, so if your data is less, right, then your neural networks are going to be overfitting, right? Because if you train them on very few samples, then you have the risk of overfitting them. So they require a sufficiently high number of samples. And that's why when the data set is large, right, like say thousands or like millions of rows, that's when you use your neural network. So always keep that in mind. When you have sufficiently large amount of data, that's when your neural networks come to the rescue, right? That's the first filter which you can always make. The second thing is the kind of feature types that you have, right? Like, are your features linear or non-linear? So when you say linear features, it means that you can model them using the relationship like y equals m1 x1 plus m2 x2 plus m3 x3 plus dot 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 plus mn xn plus b, right? So whether it's like linear regression or like say logistic regression, when you can say model your features in this way. So like long story short, if your decision boundary between your classes you believe it's going to be linear, then you can use logistic regression, right? But if you think it's going to be a non-linear decision boundary, something like this, right? In that case, you can use your SVMs, which can convert this to a linear boundary using the kernel trick, right? Using the kernel trick. So that's the second thought process, right? Then there's a concept called as interpretability. So interpretability is yeah, the ability to interpret your model. So when you convey these models, right, to stakeholders, you need to be able to explain these models. When you say explain, they need to understand like which features are important and then which features are the key features driving the performance of the model or maybe driving or make or mar the overall performance of the model. So in this case, your logistic regression wins the race because here you are basically able to explain in terms of your coefficients, like which are the driving features in your final prediction, your final binary prediction, right? Whether it's a yes or a no. What you basically do is you assign coefficients to the various features and then you transform the output using a sigmoid, right? But then at the end of the day, you are basically weighing every feature against its contribution to the model. So here, like say, suppose it's like a very default application, right? Like say you have a credit default data set, and then you have many columns here, and here the output is saying a yes or yes or no, right? Defaulted yes or no. So here it might be the loan amount, here it might be like say the number of years, here it might be like say the term, so on and so forth. So each of these features, what significance does it have to the actual default, whether it's a yes or no? That can be easily explained using logistic regression. And that's something which is really important in these kinds of applications when you convey your results to your stakeholders, right? So logistic regression wins the race here. But then when you're fine with like having a black box, right? Like when the accuracy is the only criteria, like say an image recognition application using a convolutional neural network. So here, your ability to recognize the image is the only thing that's important. You don't care about how it's recognizing that. So how it's actually recognizing that is a really complex process happening inside, because neural networks are black boxes, right? You don't know what's happening inside. You only know what is happening. You don't know how it is happening. So in such cases, you can use neural networks and go ahead with your application, right? So it all depends on what kind of uh, explainability you're considering. And then there's one last point that I want to discuss is the course of dimensionality. I'll make a separate video on this, but at the moment, just try to understand that for k nearest neighbors, right? You're trying to find out the nearest neighbor. Let's say if you have only the data on a straight line, so like these are certain points, and then these are certain points, and there's a random point here, and you're trying to find out the nearest neighbor. So it's pretty easy to find them on this line just by using one distance here, that is d, right? But then if you expand this to a two dimension, right? Let's say they look like this. So now your nearest neighbor from here is going to be maybe this guy, or say this guy, or say this guy, right? Because you have a height measure as well now. So now the measurement kind of varies now. Like if you express this in three dimensions, then it becomes even more complex to recognize the nearest neighbor. So this curse of dimensionality actually impacts the KNN algorithm, right? So you have to take that into consideration when you use KNN, right? And then there are certain aspects like fine tuning and iteration, which again, I mean, the discussion can be on and on, right? But then these are like certain points that you have to take into account when you basically choose the best model, right? Um, so yeah, here's the thing. Just think about this and let me know in your comments if you need anything else to be added to this. If you have a specific problem which you're contemplating upon and you want me to, help you address that problem. But then these are like certain high level attributes that you're taking into account when you are addressing or navigating a machine learning or a deep learning challenge, right? So I hope this was useful to all of you, and I look forward to see you in another class. Until then, I wish you best luck with your studies, and until then, take care. Bye bye. If you like this video, please press the like button. For more such videos, subscribe to the channel. If you have suggestions for a new topic and would want to see a video made on that topic, please feel free to comment in the comment section below. Thanks for watching the video and see you in another video. Bye bye.